Why do CFD simulations fail to converge? Imagine trying to balance a tall stack of blocks on a shaky table. If the foundation isn't steady, the whole thing collapses. That's similar to what happens in computational fluid dynamics simulations when they fail to reach a stable solution. One common reason is mesh quality. The mesh is like the grid that divides your model into tiny cells where calculations happen. If these cells are distorted, very long and thin, or if the sizes change abruptly, it causes numerical instability. Think of trying to walk on uneven ground. It makes progress difficult. Another factor is boundary conditions. These are the rules you set for how fluid enters and exits the system or how it interacts with surfaces. If you set impossible conditions, like a flow speed that exceeds physical limits or pressures that don't make sense, the solver gets confused and can't find a solution. Using the wrong physical models can also cause problems. For example, applying a turbulence model meant for smooth laminar flow to a highly turbulent situation can destabilize the simulation. It's like trying to fit a square peg into a round hole. Proper physics modeling is key. Solver settings play a big role too. Numerical solvers use iterative methods to find solutions step by step. If you set the relaxation factors too high or choose very large time steps, the solver might overshoot and never settle down. It's similar to trying to steer a boat with a very sensitive wheel that keeps overcorrecting. Complex geometries with sharp corners or tiny features can trap flow or cause poor mesh generation. For example, a small hole or a narrow gap between parts may not be well resolved if the mesh isn't refined enough. This can lead to unstable calculations or divergence. Initial conditions matter as well. When the simulation starts with a guess from the real flow, it can take many iterations to converge or fail altogether. Starting closer to the expected flow helps the solver find a solution faster. Residuals are measures of how well the equations are satisfied at each step. If residuals don't decrease steadily or oscillate wildly, the simulation isn't converging. This often points back to mesh issues, poor boundary conditions, or unsuitable solver settings. To improve convergence, first check your mesh. Make sure cells aren't skewed and that the size transitions smoothly. Set boundary conditions based on real physical scenarios and verify they make sense. Choose turbulence and physics models that match your flow type. Adjust solver controls carefully. Use smaller time steps and more conservative relaxation factors at the start. Simplify your geometry if possible, or refine the mesh in critical areas to better capture flow features. Providing a good initial guess, maybe from a simpler simulation, can also help. Monitoring residuals and physical quantities like forces or heat transfer rates during the run can tell you if the simulation is heading toward convergence. If residuals stay high or oscillate, revisit your mesh, boundary conditions, or solver settings. In mechanical engineering design, getting your CFD simulation to converge is essential for accurate predictions. Addressing these factors step by step makes your results more reliable and useful for making informed decisions.